All right, everybody, it's time to jump into three-dimensional vectors, okay? So I've got a vector here. This white piece of string is a vector, and this is the origin of my coordinate system. Now, what you may or may not be able to tell, so I've got a horizontal axis, this horizontal ruler here, that's my x-axis. Okay, that x might be hard to see. That's my x-axis right here. All right, and then vertically, I have the y-axis. Different courses might not have the y-axis as vertical, but that's the way I'm going to work it here. And then out of the board comes the z-axis. If this was the whiteboard here, the z-axis is coming out of the board. This is referred to as a right-handed coordinate system. And what that means, if I take my right hand and I point my fingers in the direction of the x-axis, okay, think of x, y, z, point my fingers in the direction of the x-axis, rotate my fingers in the direction of the y-axis, then z points out of the board, right? Z points towards the camera then. So that is a right-handed coordinate system. In physics and math, we use a slightly different coordinate system. Generally, z points up, x comes out of the board, and y is to the right. So x, y, z, still right-handed system. We're not going to use that as I go through these lectures, but that is oftentimes what's done. I've worked with both of them for so long that I can switch back and forth without too much trouble. So x, y, z points out of the board or towards the camera. All right, so this vector, I'm going to call that vector r, right? So that's going to be some vector r. And what I've got here is I've got r has an x component, a y component, and a z component now. So we've added a z component, right? There's an I hat and a j hat. I hat points in the direction of positive x. J hat points in the direction of positive y. And z hat points in the direction of positive z. All of those unit vectors, okay? So they have a length of 1. But now I have a z component. Another way of looking at this is with spherical coordinates, r, theta, phi. So we want to talk a little bit about what theta and phi are going to be. So phi by convention is the angle between the vector r and the y-axis. So that's the angle in here, between the vector r and the y-axis, okay? And then theta is the angle between this blue stripe, and I'll talk about that in a second, and the positive x-axis, right? The blue stripe and the positive x-axis. All right, so there's an angle in here. This points straight up and down. This post is straight up and down, so these two are parallel. And then I've cut it, so by alternate interior angles, this is phi, and this is phi, right? And so there's this projection down here. This is the projection of r onto the xz plane. So if I were to take a light, shine it from overhead, it would create a shadow down here along this blue piece of tape. And I'm going to call this the r sub xz component. It's the component of r, component of this entire vector, in the xz plane, right? And if this is the angle phi, then the sine of phi is opposite rxz over hypotenuse, which is r. And again, that's r sub x squared plus r sub y squared plus r sub z squared, all under the radical. And so r sub xz is r sine phi. Okay, r sub xz is r sine phi. All right, then if I look at the y component, because that's easy, the y component is right here, right? This is the y component, but they're the same size. This is the component of the vector r in the y direction. So this is r sub y, so would this be up to about here? Here's phi. So r is the hypotenuse. The cosine of phi is the y component divided by the hypotenuse. And so r cosine phi is the y component, and that says the x component, and that's wrong, right? So that should be the y component. Okay, so r sub y is r cosine phi. Now r sub x and r sub z, I'm going to get those by utilizing rxz and the sine and cosine of theta. So here's theta, so the x component, right, I can draw out, you probably wouldn't be able to see it anyway, but I could, here's be the y, or the z component, excuse me, and this would be the x component. So r sub xz, the x component is the cosine. Cosine of theta is the x component over r sub xz. So rxz cosine theta is the x component, right? So the x component is r x z cosine theta. Similarly, the y or the z component is r x z sine theta. The z component is r x z sine theta. Okay, and then you could put r sine phi in for r x z, and you would get the components of the vector r in the x, y, and z Cartesian system. Now in engineering, we oftentimes will also refer to as something called the directional cosines. All right, and the directional cosines, let me grab a board here real quick. The directional cosines are the cosine of the angles of the cosine of the angle in between the vector and each of the axes. So for the y component, that's real easy. It's just phi, right? And so the directional cosine, which we call lambda y, that would be just the cosine of phi. But for the x component or the z component, it's a little bit tougher to get. So if I take this board and I push it up against here, and you can't see this very well, but there's an angle along the board in between the vector r and the z axis. And there would be a similar angle, and this will be pointing down, but there's a similar angle in here between the r vector and the x axis. And lambda x and lambda z would be the cosines of those angles. So you have to think of the angle, it's not theta, right? The phi is going to handle it, but this is a different angle, it's not theta. So this would be theta z, and the angle in here would be theta x. Right? And so a lot of times you'll be working with directional cosines. I avoid them like the plague, but depending upon what book you're using or the teacher that you have, you might be working with directional cosines more often than not. All right, so there's some intro then to 3D vectors. Right? We've got a little bit of an idea of how 3D vectors work. So let's stop there, and if you have any questions, put them down in the comments below. Thank you.